All right, everybody. To talk about the Unit 5 key ideas. Unit 5 was where we really started looking at sampling distributions. And for a sampling distribution, what you do is you take many samples and record some measurement of that sample. And so to kind of take that through, just think through that bin with the red beads and the yellow beads and the white beads that I have up front if I just keep taking samples and measure something out of those samples over and over and over again, okay? And so the basic idea is sampling distributions are distributions, and when we think about those measurements that we're taking, those measurements end up being estimated. And the idea is those estimators, we measure our sample with hopes that if we've done everything correctly, our sample is a decent representation of our population. So once we've taken our sample, we have that good representation of our population. So in Unit 5, it was kind of like we knew a lot about our population, and we started exploring like what happens, what do we know about samples with respect to our population, okay? So the first thing is, the very first part of that is that we talk about biased versus unbiased estimators. So at this point, you guys are probably taking for granted p hats and x bars and all those kinds of things because we've spent so much time working on them. Okay, so like the reason we've spent so much time talking about p hat, I take my sample and I measure a proportion of my sample, and but we measure our p hats over and over and over again, right? And our goal with those p hats is every time we take one of those p hats, we're trying to figure out what p is, okay? And it turns out that for like so let's go ahead and say 25% of students are going to get a 5 on the AP exam. It's probably a little bit of a high estimator, but let's just pretend, okay? If I take a sample of, and let's go ahead and say I'm going to take a sample of 30 students, okay? So it could be that in my sample I have this guy where that sample had, I don't know, let's say 27%. 27% of that sample gets a 5 on the AP exam, but somebody else like Mrs. Turner could take a sample of the same group, right? And from the same population, and in her sample, only 23%. And then Mrs. Downer takes one, and her sample, it's 26%. So you can kind of get a feel for every single time we take these samples, all of them are pretty darn close to that population value, okay? But, we would expect to have as many above as we would have below. Okay, and whenever the mean of the population is equal to the mean of the estimator, so for instance, I didn't say that right. Whenever the mean of my sampling distribution is equal to the actual parameter, that's when we call that is an unbiased estimator. So what do I mean by that? On average, the mean of the p hats is equal to the percent of the whole population. So we can say that p hat is an unbiased estimator of p. So when we talk about bias in terms of our estimator, not all good measurements from a sample are good measurements of a population. Okay, there's some things that for the sample, the example we used in class was the range. The range of your sample is very likely to be smaller than the range of your population. So the sample range is not a good estimator of the population range. And so as you'll notice, we've spent a lot of our time talking about the sampling distribution of p hat and the sampling distribution of x bar. The reason we do that is both of those sampling distributions are unbiased. The sample means tend to resemble the population mean. The sample proportions tend to resemble the population proportion. And so what happens, that's why we care about those two estimators in particular, because they are unbiased, okay? Now, sampling variability is essentially just saying that samples are not perfect. Okay? Something that we have said over and over and over. Samples are not perfect. And so we're comfortable saying p hat is going to be close to p. We're not comfortable saying p hat is going to equal p. Okay? So some ideas, and especially now, because we'll talk about these in a lot more detail for each distribution, but we kind of, essentially, we can review this idea. Samples are not perfect, meaning that they're, like, those p hats have variability. The x bars, if we did a distribution of x bars, they would have variability. And what I want to point out is because they have variability, they have a standard deviation. I want to point out the formulas for those two standard deviations, and in particular within those formulas, I want you to see kind of two things. Both of them kind of have that square root n in the denominator, okay? And the reason that's important is if we think about that numerically, as n increases, sigma x bar or sigma p hat both decrease. And that's a big deal. Because, again, our goal, if we're trying to think about these p hats and these x bars as we're trying to estimate our population, okay? If my standard deviations, if there's less variability in my estimator, man, as n increases, we could say sigma x bar decreases is the same thing as saying that possible x bars are closer to mu. Or, and vice versa, the possible p hats are closer to p. And when you think about, like, long term, if our goal is estimating, we want our estimators to be really darn close to the value we're trying to estimate in the first place, okay? All right, now, when we talk about the distribution of p hats, I kind of have two different descriptions here. This is if I'm taking a single p hat, so we're talking about one population. And we need to think through what are those key characteristics of the distribution, again, of possible p hats. That's like when we talk about the distribution of p hats, it's a theoretical distribution of all the possible ways we could take a sample, where we have a sample of some size and a population parameter, okay? Like some population proportion that kind of describes the big ideas of what's going on. So the p hats, the shape of the p hats, you really want to be thinking about for all of these, when are they normal? Okay, so the p hats will be normal when NP and N1 minus P are both greater than or equal to 10. Okay, the center of those p hats will just be that population proportion, whatever it is. And then, like I said above, the standard deviation of those p hats is the square root of P1 minus P over N. So as we kind of think through, if you think through like possible values for this formula, like it'll be if P is equal to 0.5, that's the That's when the sigma of p hat, that's when the standard deviation of the p hats will be at its absolute largest. That'll come into play when we start talking through the finding sample size in the Unit 6 notes, okay? All right, now, if we have p hats for two populations, so for example, we might have population A and population B, and then if we're looking, then we would want to compare those two. Is there a difference between my two populations? So that one is very, very similar, right? So like that's going to be normal when NA, PA, NA, 1, like you're basically doing that NPN 1 minus P. And now you have to do it for both p hats that you're taking. But it's the same, it's that same NPN 1 minus P greater than or equal to 10 just has to be for, you have to check it for both groups. The center of P hat A minus P hat B. So start thinking through, when we think through that, okay? And here's my, so here's what we've got so far. Normal. The center is going to be PA minus PB. And I want to make sure we all understand something here, and that is when I talk about this point right here, or this point right here, any point on this graph, that point is a singular difference between two different proportions, okay? So that could be... So it's not the percent of A, it's not the percent of B, it's the difference, like I take a sample from each of them and subtracted it, okay? And then the standard deviation of P hat A minus P hat B. Now, when it comes to these formulas, these are all on your formula sheet. We'll talk about that in a lot more detail when we look at Unit 6 in terms of the application of using these things. Okay, so, but the formulas are all there on your formula sheet. So don't worry about memorizing them, just recognize like what you're filling into each place here. This is just a good kind of reminder of some of those key vocabulary words. Certainly this stuff is the leaders. All right, so similarly, we have these, the distribution of X bars, and that is going to be normal under two conditions. The easiest condition is if your sample size is large enough, the X bars are going to be normal, and our metric there is greater than or equal to 30, or we know we're sampling from a normal population. If the population is normal, then we can say the X bars will be normal no matter what the sample size will be. Now, in the, like, we're going and doing T intervals and T tests, we're checking that normal condition. When we check and we look at a graph of our sample to check our normal condition, again, we do this when our sample size is too small, what we're doing is we're basically saying, is it reasonable to believe we sampled from a normal population, okay? So if there's no major skewness or outliers in our sample, we can say, hey, our population is one where we're very likely to still end up with a normal distribution of X bars, okay? The mean of our X bars is the population mean. And like we said on the previous page, the standard deviation of the X bars is sigma over the square root of n. Okay, and similarly, if we're talking about difference between two X bars of different populations, we're going to do X bar A minus X bar B. So the situation, both of these, either of these criteria It just needs to be true for both samples. Okay, so you're going to look, and it could be like one sample is coming from a normal population, the other one is coming with a really large sample size, then that's fine. As long as one of those two conditions, one of these is true for both samples, you're fine. Okay? The mean of x bar A minus x bar B is mu A minus mu B. And again, this is like one of those things that if I were taking somebody brand new to AP Stats and I gave them this formula, this whole thing looks like really messy and scary to me, right? So one of the things, again, I want to make sure we understand is like when we use all these different notations, what does that mean, okay? So when I write this mu and then I have this subscript here, this is saying the mean of the mean of the distribution I would get if I take a sample from A, a sample from B, measure the means of both of those, okay, and subtract them. Then that would equal, then on average, those answers are going to be the difference between the two population means. So like thinking through like the notation here and what it means. All right. Now, one of the things I don't know that it has necessarily been, I feel like I've emphasized it a little bit, but not a lot of it, so I want to like really start hammering some points home here. We typically use X bars, and in general, we use these describe quantitative variables. You can't have a mean and a standard deviation of a categorical variable, right? So when we talk about the p-hats describe categorical variables. And so as I'm going through and I'm trying to decide which sampling distribution do I want to use? I want to use the one that describes the type of variable I have, okay? So, and then lastly, why do we use T for means? Okay, so we've kind of, we've talked about t-tests and z-tests and intervals and all that kind of stuff. So we only use t-intervals or t-tests when what we're doing is we're talking about a mean, okay? And so it actually stems all the way back to these sampling distributions, okay? So when we think through that, sigma of x bar is equal to sigma over the square root of n. And this formula assumes I know a lot about my population. Okay, it assumes I know the standard deviation of the population. Of course, I'll know my sample size, so I'll know n. But in reality, when we're running these tests, when we're doing a confidence interval or a test, we have to, we don't know the standard deviation of the population, okay? Because the whole idea is we don't know the population at all. So when we get into that Unit 6 and Unit 7 review, now all of a sudden I'm using S in place of sigma. And S is a bad estimator of sigma. It's not as reliable. So we don't have a choice to we don't have a choice as to whether or not we can use it, okay? Because it's all we have. So the standard deviation of your sample is just not a good estimator of the standard deviation of your population. And that's why we use T, because the T gives us a little bit more wiggle room. It accounts for this idea that we're using a not great value within our process. All right, so lastly, I have like one example here. The average time it takes a towel to air dry on a sunny day is 102.7 minutes. Okay, that's describing the mean of a population. And the standard deviation is 15.3 minutes. This would be pretty crazy that we would know this, okay? All right, so the next thing is we set up 7 towels on the clothesline. To dry. And the question is, what is the probability that the mean drying time of the 7 towels is less than 90 minutes? So as we go to do this question, I would make an argument right now. So we want to think through, so essentially we want to find the probability that X bar is less than 90. So what we would want to do then is think through, well, what do we know about the possible X bars? Well, I know the mean of those X bars is 102.7. I know the standard deviation of the X bars, right, is going to be 15.3 divided by that square root of 7. And the reason I'm doing that divided by the square root of 7 is I'm not finding, we want to think through how are the samples spread out, not the individual values, okay? Now, obviously, the teacher who wrote this problem, me, did not do a very good job because I didn't tell you overall our sample size of 7 is less than 30, and I didn't tell you the population is normal. So let's go ahead and assume that population is normal. All right, and from here, if I'm finding the probability that X bar is less than 90, this becomes a normal CDF question. So you can't see it, but I'm typing this into my calculator right now, my lower being negative a gajillion, my upper being 90, my mean being 102.7, and my standard deviation being 15.3 divided by the square root of 7. And I found that the probability that X bar is less than 90 is equal to 0.014. Not super likely. Okay, so we would expect, we would be pretty surprised if we got a sample where it took less than 90 minutes for those towels to dry. So this stuff is the foundation for what you're going to be learning, or what we do in Unit 6 and Unit 7. So hopefully this was a good review sesh, and sorry I couldn't be there. I will talk to you guys soon.